expert in quark hadron effects and crossovers. He is going to give us an overview of the neutron star equation of state. So thank you very much.
Okay, can you hear me?
Yes, thank you.
Okay. Okay, so thank you for introduction. And I'd like to thank the organizer for inviting me to this nice workshop. And today I'm going to speak about equation of state of a neutron star from the viewpoint of quantum chromodynamics, QCD, as a theory of strong interactions. And so let me begin with our motivation, one of the motivation to study neutron stars. So this is a phase diagram of QCD, which we want to determine its phase structure. So at low density and low temperature, we have a matter of hadrons. And as we heat up hadronic matter, then this hadronic matter continuously transform into a quark-gluon plasma without any phase transition. So this, although degrees of freedom look very different in hadronic phase and QGP, so actually this transition is continuous and it's crossover. And so this state of hot matter has been studied through the relativistic heavy ion collision and also by lattice QCD. And our understanding has now become matured in this region. Meanwhile, we are less confident about the understanding of region of low temperature and high baryon density, where we have a neutron star. So in order to determine the phase structure, we would like to extract some information from neutron star physics. So here is the content of my talk. So first, I briefly mention the relationship between neutron star MR relation and equation of state. And then next, I will discuss some practical modeling of equation of state based on the three-window construction. And in the third part, I will delineate the microphysics for the quark-gluon plasma, quark-hadron crossover within some schematic description. And finally, I will discuss the hyperon puzzle, which is a long-standing problem in neutron star physics and also nuclear physics. So let me begin with some overview of neutron star matter. So there are several distinct regimes. So at low density, of course, we have nuclear matter, where nucleons interact through meson exchange, or more microscopically, it is a quark exchange. And as far as our system is dilute enough, our nucleons are well-defined degrees of freedom, and nuclear matter descriptions are just fine. But beyond twice nuclear saturation density, it is well known that many body forces become very important. So that means there are many quark exchange among baryons. And with that, we naturally expect the structural change of hadrons as well as the degrees of freedom other than nucleons, such as hyperons, delta, omega, whatever. And in fact, theoretically, this regime is most difficult because degrees of freedom change from time to time. Meanwhile, this regime is most important in the context of neutron star physics. But actually, when we go beyond 5 times nuclear saturation density, our description becomes again simpler after baryons overlap, because here quarks are natural degrees of freedom. And in that sense, this regime may be regarded as quark matter. But this quark matter should be distinguished from the conventional weakly coupled quark matter, because part of the computation of QCD predict its limitation to the 40 times nuclear saturation density. And below this density, matter cannot be regarded as weakly coupled matter, but it must be strongly correlated. And in what follows, in this talk, I will mainly focus on the physics between 2 and 5 times nuclear saturation density using the hints from neutron star physics. The most basic quantity in neutron star physics is a mass-radius relation, which is determined by the balance between energy density and pressure. So for the soft equation of state, so that is, so when pressure is small for given energy density, so in that case, energy density dominates over pressure. Therefore, gravitational force is strong. Therefore, a neutron star has compact structure, and the maximum mass is also small. Meanwhile, when we discuss a stiff equation of state, pressure dominates over energy density. Therefore, a neutron star has larger radius and larger maximum mass. So this is the basic outline of the discussion. And now we can use this understanding to discuss the phase structure. For example, so if we consider equation of state having the strong first-order phase transition from hadron to quark matter, then during first-order phase transition, so pressure is constant, but energy density jump discontinuously. Therefore, during the first-order phase transition, equation of state is softened dramatically. And with that, so because of the softening, the radius of neutron star shrink radically just after the first-order phase transition. And there is some kink in the MR curve. So if we could discover this sort of kink in the MR curve, so we can conclude the existence of first-order phase transition. And another way of using this sort of discussion is nuclear matter equation of state with many-body repulsion. So basically, nuclear matter is soft matter because neutrons are heavy. And in order to change this property, we need to rely on the 2 or 3-body repulsion. And the characteristic of this sort of soft matter, nuclear matter, is initially at low density, equation of state is very soft. That is a non-relativistic matter. And because of the many-body repulsion, it gradually stiffens at higher density. But this stiffening is rather slow because the many-body repulsion grows with power. So for the 3-body forces, it grows like N2 cube. But its growth is slow. Therefore, before reaching this stiff domain, the nuclear equation of state remains soft. That's the reason why typically nuclear equation of state has a smaller radius. And as we go to higher mass region, equation of state becomes stiffer and eventually pass the two-third mass constraint if we arrange repulsion properly. This is a typical trend of the nuclear equation of state, relying on the many-body repulsion. But on the other hand, neutron star observation seem to suggest that the equation of state stiffen radically, somewhere around 2 to 3 times nuclear saturation density. And so this kind of implication comes from the measurement of NICER for 1.4 and 2.1 solar mass neutron star, the historical detection of gravitational wave, and also the improved nuclear constraint at low density. And all information, putting all this information together, so it is likely that 1.4 and 2.1 solar mass neutron star have the similar radius like this. And this sort of behavior, similar radius, require a rapid stiffening at relatively low density. And this kind of trend is difficult to reproduce using usual hybrid equation of state with first-order phase transition. Or it is also difficult to explain using the nuclear model with many-body forces because its stiffening is rather slow. And when the neutron star mass reaches a two-third mass region, radius becomes already small, rather small. And the central question for the QCD community is to explain how to describe, how to understand this rapid stiffening at the density not so far from the nuclear saturation density. And let me briefly mention, this kind of rapid stiffening it has been also indicated from the various statistical inference methods like Bayesian or deep learning method on the sound velocity square, which is the dPd epsilon. And so those statistical analysis utilize as a prior, they utilize the information from chiral EFT, astrophysical constraint, causality, and also part-adaptive QCD constraint at high density. And together, putting them together, the typical trend is the rapid stiffening somewhere around 2 to 3 times nuclear saturation density. And but NICER's observation have still systematic error, and we are looking forward to some the news from the neutron star merger community on the high mass neutron star. So binary neutron star merger already gave us a lot of important information, like tidal deformability or kilonova constraint for the maximum mass of neutron star. But what we are really interested in is the post-merger signal, which is strongly correlated to the information radius of a high-mass neutron star. So post-merger signal has some typical frequency. So post-merger, the merged object have some rotation and vibration that produce some fundamental oscillation. And we are particularly interested in the so-called F2 peak. And this effective frequency has strong correlation with high mass neutron star radius. And what we are really interested in is a contrast between the radius of 1.4 and radius of 2.2 solar mass neutron star. And we want to have the similar, we want to confirm whether this radius is really similar or not. And this information can be actually strongly correlated with the correlation between tidal probability lambda and F2 frequency. So lambda has strong correlation with the radius of 1.4 solar mass neutron star, and F2 frequency has strong correlation with the radius of high mass neutron star. And so by looking at lambda F2 correlation, we can infer the correlation between 1.4 and 2 solar mass neutron star radius. But anyway, this is what we want to know in the future. And so let me now move to some practical modeling of equation state based on three-window picture. So this three-window picture is just relying on some basic understanding, so natural understanding of the effective field theory. So any effective theory has a domain of applicability. So in the case of a nuclear equation state, so we can trust a nuclear equation state only up to, let's say, 1.5 or twice nuclear saturation density. And we should stop using, for example, chiral AFT up to this point. Meanwhile, at higher density, so at high density, we expect some quark matter. But the quark matter picture is valid only beyond some density, let's say around 4 to 5 times saturation density. Therefore, we use the quark model only beyond such density. So, and so having these two boundary, so we use this two equation state just as a boundary condition, and then consider many possible interpolating curve. And so we make this interpolation smoothly. So we require pressure and first derivative and second derivative to be smooth at each boundary. So therefore we have 6 boundary conditions. So therefore we used the 6th order polynomial with 6 boundary conditions. Therefore each coefficient can be determined completely. And if you want to describe the first order phase transition, as an option we can put a small kink somewhere. And so, and this is some just a phenomenological interpolation. Therefore, many people would think that so there are a lot of liberty to connect these two equation state, but actually there is actually that's not easy. The interpolation is not easy at all. So in fact, so this domain has a strong correlation because when we construct interpolation, we have to satisfy the causality constraint, and also we have to satisfy some stability conditions. And with that condition, so low density and high density domain actually have the strong correlation. So they are not independent of each other. So once we fix a nuclear equation state at low density, actually we don't have much freedom for the construction of quark matter here, and also for this interpolating curve. So the causality constraint and also two-solar mass constraint gives a strong constraint on the equation state, not only for interpolated region, but also for quark matter region. And typically, the allowed band, the range of this uncertainty band is about 10 to 20% of the total pressure. So, so by just this methodology, there is strong correlation. But actually, we further impose some physical insight based on the common sense for the hadron physics. So because we are looking at quark matter around 5 times saturation density, and this density is roughly about the density inside of a single baryon. Therefore, we should consider the quark model based on the hadron phenomenology. And that motivates us to use some quark model, which is based on the hadron physics. And therefore, our construction of Hamiltonian is like this. So first term comes from the chiral dynamics of QCD or hadron physics, and whose parameters are completely fixed in the vacuum phenomenology. And in addition to that, there are several interactions which become increasingly important at high density in the relativistic regime. The first example is color magnetic interaction, which becomes stronger at high density. And another important possible interaction is density-density repulsion, which is motivated by the hardcore repulsion or omega meson exchange in nuclear physics. So H and GV are new free parameter which we introduced. and we construct many equation of state as a function of H and GB. And having fixed the effective Hamiltonian, we solve this Hamiltonian within the mean field approximation, imposing color and charge neutrality condition as well as beta equilibrium condition. And then now we construct the unified equation of state as a function of GB and H. Those are only free parameters in our model construction. So let me summarize the step we should take. The first step is to choose the realistic nuclear equation state for low density. So example are the APR or Togashi or chiral EFT at the next to leading order. And around saturation density, the uncertainty of the pressure is about 10 to 30%. And choosing one nuclear equation state, then we consider many possible quark matter model as a function of GB and H. But in fact, the allowed range of GB and H are strongly limited by the causality and stability condition like this. Okay, so looking at the magnitude of H and GB, that is typically the order of 1. And on the other hand, so allowed the allowed range of variation is order 0.5 or something, or 10%, and that is reflected to the uncertainty in the pressure. In what follows, within this band, we consider what is the possible MR relation or not, and as a function, it depends on our choice of nuclear equation state. And so this is the mass radius relation. And so here we exhibit two examples using the two different nuclear equation state. So Togashi nuclear equation state and chiral EFT at low density. And the first point I want to make is basically the radius of 1.4 solar mass neutron star is basically determined by our choice of nuclear equation state. Meanwhile, the radius and the maximum mass of neutron star, high mass region of neutron star, basically strongly depends on our choice of quark model parameter. And the general trend is, so compared to the purely nuclear equation state like this, okay, the equation state using the quark matter model at high density has typically have a rapid stiffening around 2 to 3 times nuclear saturation density, and it make a peak in the sound velocity square. And so because nuclear equation state stiffen rather slowly, so when we look at the high mass region, the radius tend to be smaller compared to the model having the rapid stiffening around at the low density region. So this is a typical trend of the crossover equation state. So sound velocity peak is a typical trend for crossover equation state. But so far, my discussion is so phenomenological, and we would like to understand what is the microscopic mechanism to generate this sound velocity peak. So what is the origin of this rapid stiffening? So that's the topic I would like to address in the next section. So next, I want to discuss some concrete realization of rapid stiffening. The problem we would like to address is this rapid stiffening somewhere around 2 to 3 times nuclear saturation density. And so in order to explain it, so the first thing I want to emphasize is the stiffness of quark matter. So usually when we discuss quark matter equation of state, usually it is often discussed in the context of soft equation of state because it is usually combined with hybrid equation of state with first order phase transition. But in general, quark equation of state have the more ability to generate a stiff equation of state. So that's the first thing I want to emphasize. The simplest possible equation of state is actually should be the free massless quark gas, which is given by whose pressure is given by just 1/3 of the energy density. And so actually, so whenever we construct equation of state, we have to put some normalization constant to make the set 0 for the pressure. And actually, even though quark equation of state have the ability to generate stiff equation of state, so depending on our choice of normalization constant, it can be either stiff or soft. And if we choose sufficiently small bug constant or normalization constant, actually maximum mass can be can be as large as 3 solar mass, okay, even without any interaction. So that is the example why quark matter equation state may be regarded as stiff. But intuitively, this should not be too surprising because quark matter with small mass, okay, with a quark with small mass is relativistic particle, and they can move very rapidly. And so we naturally expect large pressure or large kinetic energy. What obscure this picture is actually this Planck constant. And if we choose very large Planck constant, then the neutron star mass becomes smaller, and the equation of state is also smaller, softer. But what I want to emphasize here is quark matter can be a potential good starting point to construct a stiff equation of state. And so this normalization issue is actually serious when we try to construct a hybrid equation of state, which is a combination of hadronic equation of state at low density and quark matter equation of state at high density. So the problem is, so when we when we prepare the hadronic and the quark equation of state independently from the two independent model, then there is no way to fix the relative normalization constant because they are based on two different models. So it is difficult to fix the normalization constant. And depending on our choice, so if we choose a large Planck constant, then quark equation of state is soft, and we can construct a model first order phase transition. But if we choose a rather small Planck constant, then we rather have the crossover picture. And it is very difficult to pin down which relative normalization constant is correct. And in order to avoid this sort of uncertainty, so we have to use just a single model. And using single model, there is one normalization, okay? And there is no issue about this sort of uncertainty. But to do that, we have to keep track of quark state all the way from nuclear matter region to quark matter region. And so that's what I want to discuss in the following. But before doing that, so let me emphasize the role of confinement. So, so because of confinement, quarks are confined into baryons, and that makes the baryonic matter. But when we look at the quark inside of baryonic matter, so since quarks are confined within some small domain of size scale of order 1 Fermi, the kinetic energy of quark or momentum of quark is relatively high, of order 200 to 300 MeV. So quark can move relativistically. But this large kinetic energy and large mechanical pressure inside of baryons actually do not contribute to the thermodynamic pressure. So quark kinetic energy is basically absorbed into the mass of baryon. Okay, so it does not leak out as a pressure. Okay, and on the other hand, center of mass energy is suppressed by the inverse power of the baryon mass, and that is of course much smaller than the baryon mass. So therefore, center of mass energy is small. Therefore, energy density is dominated by the mass energy, which is much bigger than the pressure made of corrective motion of baryon. So in other words, so quarks are relativistic, but confinement allows a quark to appear only in energy density, but confinement does not allow a quark to contribute to the pressure, and that's the reason why baryonic matter is so soft. Then a natural question is, when do quarks begin to contribute to the thermodynamic pressure? So that is a central question I would like to address. And so, because I emphasize, we are looking at some domain between nuclear matter and quark matter, and there are issues about confinement. So we would like to discuss some concrete model of crossover based on confinement, which maintain the confinement property. And one of the description for the crossover region is so-called quarking matter, for which people make a different definition for different people. But my definition is very simple. So quarking matter is basically quark matter, but they still have a confining gluon that trap quarks into baryon. Okay, and so let me consider how nuclear matter evolved into the weakly coupled quark matter. So at very low density, the matter is simply made of a composite particle, that is baryon. So baryon make Fermi C. But when we increase the density, then eventually, initially, quark Fermi C is developed at the inside of the baryonic Fermi C, as I will explain later. And if we keep increasing the density, then quark Fermi C dominates the bulk property of matter. But we still have a confining gluon. Therefore, excitation on top of quark Fermi C is confined, and that is hadronic. So in that way, there is a baryonic Fermi surface on top of the quark Fermi C in the bulk, and this sort of matter is called quark matter. And as we increase density further and further, then eventually gluons are screened by device screening, and then gluons which are responsible for component becomes weakly coupled. Therefore, the quark Fermi C is dominant, and we have a weakly coupled Fermi C surface on top of the quark Fermi C, and this is a weakly coupled quark matter. So what I would like to discuss is this intermediate domain from nuclear matter to quark matter. And in order to describe this state of matter, there should be some simple description to represent the key idea. And so recently, we constructed a simple model which reflects the confining property of matter. So, of course, many-body problems are so complicated. So therefore, we want to adapt some sort of a coarse-grained description. So that is, we will characterize the state of matter by just looking at how quark states are occupied and how baryonic states are occupied in dense matter. And so there are three important ingredients for that description. The first ingredient is a quark momentum distribution or wave function inside of a single baryon. And so this kind of information can be derived by solving a three-body problem for a single baryon. So this is doable. Meanwhile, another important information is how baryonic states are occupied. So in the case of ideal baryon gas, so baryons occupy states from 0 to Fermi momentum with probability 1 and make baryonic Fermi C. And so, now, so we pick up a quark contribution from each baryon one by one, and then by convoluting it, so we can extract information about how quark states are occupied in dense matter. And in the case of ideal baryon gas, so basically, quark distribution in many-body system have the similar shape as the quark distribution inside of a single baryon, but its magnitude actually is scale like the density. So as we increase the baryonic Fermi C, size of baryonic Fermi C, so quark distribution, its magnitude keep growing in the in vertical direction. So this is a basic scaling behavior in baryonic matter. So now I would like to discuss the evolution from nuclear matter to quark matter. So as I said, in dilute regime, we have a baryonic Fermi C and the quark distribution scale like this. But as we increase density, as I said, so this magnitude keep growing proportionally to the density. But since this FQ is a probability, therefore there is an upper bound. So when density is high enough, the quark state at low momentum become fully saturated, and we call it a quark saturation. And after quark states are fully saturated at low momentum, so we can no longer keep increasing the baryon Fermi C like this. But now we have to put the baryonic state, baryons, to the high momentum. And we have to under-occupy the baryonic state at low momentum. Otherwise, it would violate the Pauli principle at low momentum. And this is a key feature of key observation, and which reproduced the famous McLaren paper for quark matter. So basically, by putting a baryon at high momentum, while density is not so high, so we have more portion of the high energy baryons, and that's naturally a Stephen equation state. So this looks very exotic in baryonic language, but if we look at the quark matter language, so it is rather easy to imagine. So quark states are fully occupied, and it develops the quark Fermi C. And on top of that, we have baryonic correlation. But we have already discussed the quark matter scaling can generate the Stephen equation state. And so in either in baryonic language or in quark language, we can discuss the Stephen equation state. And then the natural question is when does quark saturation happen? And if we choose the size of baryon to be of order 1 Fermi, 0.5 to 1 Fermi, then this Cox saturation is estimated to occur around somewhere around 2 to 3 times nuclear saturation density. That's what we wanted. So there is an early stiffening before many body forces of nuclear forces set in. And this is another schematic summary. So this is pressure versus energy density. So if we keep if we pretend baryonic descriptions are valid forever, then baryonic equation state remain very soft. In order to change this situation, many people introduce many body repulsion to make equation state stiffer. Meanwhile, before this many body force dominate, quark saturation set in, and because of quark saturation, the matter is forced to transform into quark matter regime. And in this transient regime, we have the rapid increase of pressure, and this is called the peak in the sound velocity. And this stiffening is inevitable because it is based on the quark principle. And the final topic I would like to discuss is the Hyperon puzzle, which is a long-standing problem in nuclear physics and also neutron star community. So, but before that, let me extend the previous discussion for the multiplier, including strangeness. So multiplier extension is actually quite straightforward. So what we have to do is just put many baryon species like proton, neutron, lambda, sigma minus, or omega, whatever, and then sum up all baryonic contribution, and then sum up all quark contribution inside each baryon. And then we can construct how quark state, we can evaluate how quark states are occupied. So then at some point, quark states are fully saturated, and then there emerges some non-trivial correlation among different baryon species statistically. So even without including any baryon-baryon interaction explicitly, this statistical constraint generates some non-trivial correlation between different baryon species. And I would like to utilize this correlation to mitigate the problem of a Hyperon puzzle. So what is Hyperon puzzle? So Hyperon puzzle is a softening of equation state. So whenever Hyperon appear, so they initially at threshold, at just the onset of the Hyperon, so first they appear as a non-relativistic particle. So therefore it has large energy density through the mass, but it does not have kinetic energy. So it gives just a small pressure. Therefore equation state radically soften. So this is the problem. And the current state-of-art calculation based on the empirical Yn and Yn many-body repulsion barely satisfy the two-solar mass constraint and also radius constraint. So, but on the other hand, the discussion relying on the three-body repulsion always leaves some question concerning the convergence of many-body forces. So therefore, we want to supply some alternative idea based on the quark saturation, which should help this sort of discussion in addition. And the advantage of the quark level discussion is it is firmly supported by the statistical repulsion because it is based on the quark principle. And this repulsive effect becomes stronger and stronger at higher density because more quark states are saturated at higher density. And finally, since we are talking quarks explicitly for each baryon, so therefore there is no worry about double counting. So let me briefly demonstrate some calculation using just considering the simplest kind of matter, n lambda zero matter, both of baryons are charge neutral. And in conventional picture, as we increase neutron density, neutron Fermi energy keep increasing, and at some point it goes beyond the mass of lambda zero. And then energetic neutron start to decay into a low energy or low momentum hyperon. And since these hyperons are non-relativistic, therefore equation state are softened dramatically. So this is the original problem. And if we don't introduce strong repulsion between Yn and Yn repulsion, then this sort of conversion occur somewhere around 2 to 3 times nuclear saturation density. But when we take into account the constraint from the quark saturation, then actually this sort of decay is forbidden. So suppose d quark states are already saturated in dense neutron matter. And let us imagine the energetic neutron decay into low momentum hyperon. But this low momentum hyperon also contains d quark. So therefore, through this conversion, the d quark states are increased at low momentum, and it would violate the Pauli principle for d quark. So this kind of conversion is not possible in the presence of d quark saturation. So how hyperon can emerge in the system? So actually, there must be some extra process. So in order to generate the hyperon at low momentum, the first thing we have to do is to open the phase space for d quark. And so this can be possible by replacing one neutron with one single lambda zero. And since a neutron contains two d quark, and while lambda contains only one quark, so this replacement of a neutron with hyperon can open the phase space for d quark at low momentum. And then now d quark phase space is available at low momentum. So therefore, energetic neutron now can decay into the low momentum hyperon until d quark states again get fully saturated. So this is the extra process we needed to generate hyperon. And obviously, replacement of neutron with lambda zero cost energy m lambda minus mn. So this energetic cost require more chemical potential, baryon chemical potential to generate hyperon. And therefore, it also requires higher density to generate hyperon in the system. And this is one model calculation. So in this model calculation of quark matter, so we have the quark saturation somewhere around 2 to 3 times saturation density. And after d quark saturation, equation state stiffen like this. And d quark saturation also the delay the appearance of hyperon. So without d quark saturation, the lambda zero would appear somewhere around twice nuclear saturation density in this model. But by putting d quark saturation, the hyperon appear only beyond 5 times nuclear saturation density. And even though in this calculation, we didn't include any baryon-baryon interaction or YN repulsion, but the statistical consideration alone have some significant impact. And of course, realistically, this sort of discussion should be combined with more realistic modeling based on the empirical YN forces. But the discussion based on quark should be implemented to finalize the conclusion. So that's our statement. And let me summarize my talk. So as I emphasized, the relation between 1.4 and 2.1 solar mass neutron star radius. So this is really important to discriminate different modeling and different picture of and also phase structure. And it is very important to establish this sort of relation. And the neutron star merger simulation for the post-merging phase should be very important, especially to confirm the large radius of 2.1 solar mass neutron star. So that is what I'm looking forward into the future simulation. And quark degrees of freedom. So I try to convince you quarks are very important. And quark degrees of freedom are important even before the confinement happens. So even in nuclear matter or baryonic matter region, we should take into account, we should have some discussion in which the quark description gives some important constraint for the baryon dynamics. And the interplay between nuclear and the quark matter domain actually are very important. So they are not a separated issue, but they should be considered together always. And in fact, because of causality and thermodynamic stability, they constrain each other rather strongly. That's the message I would like to address in my discussion for the three-window modeling. And finally, so quark degrees of freedom can give some new way of thinking to mitigate the hyperon puzzle. And with that, so I conclude my talk, and thank you very much for your attention. Thank you very much.